Have you ever considered the intricate choreography of water and air that occurs with every simple push of a handle in a public restroom? Beneath the unassuming surface of a commercial toilet, a precise mechanism operates, engineered not just to dispose of waste, but to do so with increasing efficiency, a testament to decades of subtle, often overlooked, standardization. It's a journey from a gushing deluge to a measured stream, a transformation driven by evolving environmental awareness and diligent engineering. To truly understand its significance, we need to examine its origins and its gradual, deliberate evolution from the 1970s through the end of the millennium. Our journey into the nuanced world of commercial restroom toilet flush valve designs and water efficiency regulations in American public buildings begins in the comparatively less regulated era of the early 1970s. At this time, the prevailing mindset regarding water usage in commercial facilities was largely one of abundance. The concept of water as a finite resource, requiring careful conservation, had not yet permeated the collective consciousness to the extent it would in later decades. Consequently, the flush valves installed in public buildings across the United States were often designed with generosity in mind, prioritizing powerful, unequivocal waste removal above all else. These systems typically consumed anywhere from 3.5 to a substantial 5.0 gallons of water per flush, and in some older installations, even more. The predominant technology of the era was the flushometer, specifically the diaphragm-type flushometer. This device, a marvel of simple yet effective hydraulic engineering, operated on the principle of balanced water pressure. Within the main body of the flushometer, a flexible diaphragm, often made of a durable rubber compound, divided two chambers. When the toilet was at rest, water pressure from the supply line was applied equally to both sides of this diaphragm, holding it in a closed position and preventing water from flowing into the toilet bowl. The magic of the flush began when the handle was pressed. This action momentarily opened a small relief valve, allowing a small amount of water to escape from the upper chamber of the diaphragm. The instantaneous reduction in pressure above the diaphragm caused the higher pressure from the supply line, acting on the underside of the diaphragm, to lift it. This lifting action opened the main water pathway, allowing a rapid, high-volume surge of water to enter the toilet bowl, initiating the flush cycle. Once the predetermined volume of water had passed, usually dictated by the size of a bypass hole in the diaphragm that slowly allowed water pressure to equalize above it again, the diaphragm would gently descend, closing the main valve and stopping the flow of water. Each component played a vital role. The control stop, often located on the side of the main valve body, regulated the flow rate and allowed for maintenance isolation. The vacuum breaker prevented the undesirable siphoning of used water back into the potable water supply, a critical public health safeguard. And the handle assembly served as the user interface, a simple lever activating a complex hydraulic sequence. These systems, while effective, were not built with water conservation as a primary design criterion. During this nascent period, the regulatory landscape for plumbing fixtures, particularly in commercial settings, was highly fragmented. There was no overarching federal mandate dictating water efficiency standards. Instead, oversight was primarily relegated to local and, to a lesser extent, state plumbing codes. Organizations such as the International Association of Plumbing and Mechanical Officials, or IAPMO, had developed the Uniform Plumbing Code, or UPC, which provided a comprehensive set of guidelines for plumbing installations. While influential, the UPC in the early 1970s was focused more on safety, sanitation, and proper installation practices, rather than stringent water conservation. Adoption of such codes varied significantly from one jurisdiction to another, leading to a patchwork of standards across the nation. A toilet flush valve, installed in a public building in California, might consume a different volume of water than an identical model installed in New York, simply due to differing local codes or the absence of specific efficiency requirements. This regional variation underscores the incremental nature of the changes we are about to explore, as the move towards national standardization was a gradual and often challenging process. As the decade progressed into the mid to late 1970s, the first faint murmurs of change began to emerge. Environmental consciousness, spurred by events like the first Earth Day in 1970, began to slowly seep into public discourse, extending beyond broad ecological concerns to more specific matters of resource management. Water, once taken for granted as an endlessly renewable resource, started to be viewed through a slightly different lens in certain regions. A pivotal factor in this nascent shift was the occurrence of significant drought conditions in various parts of the United States, most notably in California during the mid-1970s. These droughts brought the issue of water scarcity into stark, undeniable relief, compelling communities and policymakers to consider conservation measures that had previously seemed unnecessary. It was against this backdrop that some pioneering local and state governments began to explore the concept of reducing water usage in plumbing fixtures. While still far from widespread federal mandates, these early initiatives represented the first tangible steps toward what would become a decades-long pursuit of efficiency. Jurisdictions like California, grappling directly with water shortages, started to investigate the feasibility of lower flush volumes for toilets, recognizing that even small reductions per flush, multiplied across millions of uses in commercial and residential settings, could yield substantial overall savings. Massachusetts also emerged as an early adopter of more stringent water-saving regulations. These initial pushes were often tentative, experimental, and met with varying degrees of resistance, both from the manufacturing industry, which faced the prospect of redesigning established products, and from the public, accustomed to powerful, high-volume flushes. In response to these nascent pressures, manufacturers of flush valves and vitreous china plumbing fixtures began a period of cautious technological exploration. Engineers started to experiment with subtle modifications to existing diaphragm-type flushometers. This included investigating smaller diaphragms, adjusting the size of the bypass holes that controlled the repressurization rate, or subtly altering the internal geometry of the valve body to affect flow characteristics. The goal was to reduce the volume of water dispensed per flush without compromising the critical function of waste removal. Early concepts of pressure-assisted flushing mechanisms also began to surface during this time, though their widespread adoption and refinement were still years away. These early explorations represented a slow but deliberate shift in design philosophy, moving from an unconstrained flow paradigm to one where the judicious use of water was starting to be factored into the engineering equation. Within professional organizations and industry associations, discussions around water conservation gained a quiet but steady momentum. Plumbing engineers, architects, building owners, and manufacturers gathered to discuss the technical challenges and opportunities associated with reducing water usage. A recurring concern was the delicate balance between water savings and effective performance. There was a legitimate fear that simply reducing flush volume without corresponding innovations in bowl design or flush valve technology could lead to unsatisfactory performance, such as incomplete waste removal or increased clogging, which would ultimately negate any intended water savings through multiple flushes. These discussions underscored the fact that true water efficiency would require a holistic approach, considering the entire toilet system rather than just isolated components. This period, therefore, can be characterized as one of foundational inquiry, where the seeds of future standardization efforts were being planted, nurtured by growing environmental awareness and the practical lessons learned from regional water crises. As the 1980s unfolded, the efforts toward water conservation began to crystallize into more formalized processes, driven significantly by the vital work of standardization bodies. Among the most influential of these were the American Society of Mechanical Engineers, or ASME, and the American National Standards Institute, or ANSI. These organizations, through their established frameworks for developing voluntary consensus standards, would play a crucial role in shaping the future of commercial plumbing efficiency. ASME, with its long history of engineering expertise, took the lead in developing specific performance criteria for plumbing fixtures. This involved the formation of technical committees, composed of a diverse group of stakeholders, including representatives from plumbing manufacturers, independent testing laboratories, plumbing engineers, building code officials, and government agencies. This collaborative approach ensured that any proposed standard was robust, technically sound, and achievable by the industry, while also addressing public health and safety concerns. A key output of these collaborative efforts was the development of specific standards that would define the performance parameters for toilets and flush valves. Two particularly relevant standards that emerged from ASME during this period were ASME A112.19.2, titled Vitreous China Plumbing Fixtures and Hydraulic Requirements, and ASME A112.19.6, which focused on hydraulic performance requirements for water closets and urinals. These documents were not merely suggestions, they detailed precise testing procedures that manufacturers had to follow to demonstrate compliance. They established criteria for essential performance aspects, including the actual flush volume, the ability to effectively remove solid waste, and the efficacy of bowl cleaning. For instance, testing protocols would specify the use of certain artificial waste materials to simulate real-world conditions, and measurements would be taken to ensure that a specified percentage of this waste was reliably removed from the bowl in a single flush. These standards provided a common language and a common set of benchmarks for the entire industry, allowing for comparison and driving innovation. Against this backdrop of formalized standardization efforts, the concept of low-flush plumbing fixtures gained significant traction. While still a relative term compared to later standards, the industry began to coalesce around targets such as 3.5 gallons per flush, a notable reduction from the often 5.0 GPF or higher volumes prevalent just a decade prior. This target was seen as a pragmatic balance between achieving meaningful water savings and ensuring acceptable performance with existing or slightly modified technologies. The pursuit of this 3.5 GPF standard was driven by a growing awareness that water resources, even in seemingly abundant regions, were coming under increasing strain due to population growth, industrial demand, and agricultural needs. Concurrently, a growing chorus of advocacy groups, environmental organizations, and certain progressive states began to exert pressure for federal action. They argued that a fragmented, state-by-state approach to water efficiency would be insufficient to address the national challenge of water conservation. A federal mandate, they contended, would create a level playing field for manufacturers, simplify compliance for builders, and accelerate the widespread adoption of water-saving technologies across the entire nation. This period, therefore, set the stage for a truly transformative shift in how water-using plumbing fixtures, particularly commercial flush valve toilets, would be designed, manufactured, and regulated in the United States. The groundwork laid by ASME and ANSI through their meticulous standard-setting processes provided the technical and procedural framework upon which future federal mandates would be built, ensuring that when policy decisions were made, they rested upon a foundation of engineering principles and demonstrable performance criteria. This deliberate, consensus-driven approach to standardization was a hallmark of the incremental progress that defined this era. The culmination of these early efforts and growing awareness arrived with what can unequivocally be described as a watershed moment for water efficiency in American public buildings. The passage of the Energy Policy Act of 1992, widely known as EP Act 1992. This landmark federal legislation was not solely focused on water. Rather, it was a comprehensive bill designed to address broader energy and environmental concerns across various sectors of the economy. However, embedded within its extensive provisions were specific, legally binding mandates for water-using plumbing fixtures, which would fundamentally alter the landscape for commercial restrooms. The most impactful provision of EPAC 1992, pertaining to our discussion, was the mandate that all toilets manufactured in the United States after January 1, 1994, both residential and commercial, could not exceed a flush volume of 1.6 gallons per flush, or GPF. This represented a substantial reduction from the prevailing 3.5 GPF standard that had begun to gain traction in the 1980s, and an even more dramatic cut from the 5.0 GPF or higher volumes common in the 1970s. The selection of 1.6 GPF was not arbitrary. It was the result of extensive scientific research and engineering deliberations, balancing the imperative for significant water savings with the practical necessity of ensuring effective waste removal. Engineers and policymakers aimed to identify the lowest flush volume that could consistently perform without leading to widespread dissatisfaction or systemic plumbing issues, drawing upon the insights gained from the SME standards development process. The implications of this mandate for commercial flush valve design were profound and immediate. Manufacturers of flushometers, such as those made by companies like Sloan and Zurn, which dominated the commercial market, faced the considerable challenge of re-engineering their well-established diaphragm valve systems to meet the new, more stringent 1.6 GPF requirement. This was not a simple matter of swapping out a component. It demanded a fundamental rethinking of the flush cycle's hydraulics. The focus shifted intensely toward ensuring the most efficient possible delivery of water into the toilet bowl. Engineers had to meticulously optimize the timing of the flush, the velocity of the water stream, and its distribution within the bowl to maximize its cleaning and waste removal capabilities, all while using less than half the water of previous models. One of the most significant technological responses to the 1.6 GPF mandate, particularly in commercial settings, was the increased adoption and refinement of pressure-assisted flushometers. Unlike gravity-fed toilets, which rely solely on the weight of water to create a siphonic action, pressure-assisted systems harness compressed air to force water into the bowl at a higher velocity. These systems typically incorporate a sealed plastic tank, often located within the toilet's vitreous china tank, or integrated into the flush valve mechanism, which traps incoming water and compresses the air above it. When the flush handle is activated, this compressed air rapidly expels the water into the bowl, creating a powerful, vigorous flush. The advantages were clear: a stronger, more consistent flush, often resulting in a cleaner bowl and a reduced likelihood of clogs, all while meeting the 1.6 GPF standard. However, these systems also presented some disadvantages, including increased noise during flushing, a higher initial cost, and slightly more complex maintenance due to the additional components. Nevertheless, their superior performance in high-traffic commercial environments often justified their adoption. Beyond the flush valve itself, the mandate also necessitated a parallel evolution in toilet bowl design. Engineers collaborated closely with industrial designers to optimize the vitreous china fixtures that the flush valves served. Critical design elements included wider trapways, which are the convoluted internal passages through which waste exits the bowl. Increasing the diameter of the trapway helped to prevent blockages, especially when dealing with a reduced volume of water. Improvements in the quality and application of surface glazing made the interior of the bowls slicker, reducing friction and allowing waste to be carried away more effectively with less water. The design of the rim jets and siphon jet, the small openings around the rim and at the bottom of the bowl that direct water into the trapway, was also meticulously refined to create the optimal siphonic or washdown action for thorough waste removal at the new, lower flush volume. The interaction between the flush valve and the bowl became a tightly integrated system, each component optimized to compensate for the reduction in water. Furthermore, ancillary components of the flushometer system also required optimization. The control stops, which regulate the incoming water flow and pressure, and the vacuum breakers, essential for preventing backflow, had to be redesigned or fine-tuned to ensure compatibility with lower flow rates and pressures while maintaining their critical functions. This period also saw the slow but steady emergence of sensor-activated flush valves, particularly in higher-end commercial installations. These touchless systems, relying on infrared or other motion-sensing technologies, introduced new layers of engineering complexity, requiring electronic components to reliably trigger the mechanical flush valve mechanism at the appropriate time. The integration of these electronic controls with the hydraulic demands of the 1.6 GPF standard was an additional design challenge. In essence, EP 1992 was not just a regulation, it was a catalyst for fundamental innovation. It forced the plumbing industry to rapidly accelerate its research and development efforts, pushing the boundaries of what was technically feasible in water-efficient fixture design. The compliance deadline of January 1, 1994, created an urgent imperative for manufacturers to adapt, leading to a decade of intense product development and refinement, as the industry grappled with the implementation challenges and sought to overcome the initial performance hurdles of this significant regulatory shift. The ripple effects of this legislation would continue to be felt and refined throughout the remainder of the 1990s and well beyond, establishing a new baseline for water conservation in American public buildings. The immediate aftermath of EP Act 1992's implementation, particularly in the mid to late 1990s, was characterized by a period of both significant innovation and considerable growing pains. While the intention behind the 1.6 GPF mandate was unequivocally positive from an environmental perspective, the initial transition was not without its challenges, particularly regarding fixture performance. Many early 1.6 GPF toilets, especially some of the first-generation residential gravity-fed models, suffered from what became colloquially known as the 1.6 GPF blues. These early versions sometimes struggled to effectively remove waste in a single flush, leading to consumer dissatisfaction and, paradoxically, often resulting in multiple flushes per use, thereby negating some of the intended water savings. This performance deficit highlighted the complexities inherent in such a drastic reduction in water volume. However, the commercial sector, while not entirely immune to these issues, had some distinct advantages that made its transition potentially smoother than the residential market. Commercial toilets, particularly those in high-traffic public buildings, had historically relied on flushometers, which typically operated with higher water pressures than residential tank-type toilets. This higher inherent pressure provided a stronger initial push of water, which, when combined with optimized flush valve and bowl designs, could more effectively compensate for the reduced volume. Nevertheless, performance remained a paramount concern in high-use commercial environments, where reliability and efficiency were critical for maintaining hygiene standards and minimizing operational disruptions. Building managers and owners were understandably wary of adopting fixtures that might lead to increased maintenance calls or user frustration. In response to these early performance issues, the plumbing industry embarked on a concerted effort to refine and innovate. Manufacturers invested heavily in research and development to address the perceived shortcomings and improve the reliability of 1.6 GPF fixtures. This renewed focus led to a period of intense redesign and innovation, where every aspect of the toilet system was re-examined. Engineers realized that merely reducing water volume was insufficient. The entire hydraulic system, encompassing the flush valve and the toilet bowl, needed to be optimized to work synergistically. One critical area of focus was the toilet bowl's trapway diameter. A wider trapway provided a less restrictive path for waste, significantly reducing the likelihood of clogging, which had been a major complaint with some early low-flow models. While early 1.6 GPF designs sometimes used smaller trapways to try and improve velocity, the industry quickly learned that a larger diameter, combined with proper water delivery from the flush valve, was key to reliable waste removal. Concurrently, advancements were made in the quality and application of surface glazing inside the toilet bowl. Improved glazes created a smoother, more hydrophobic surface, reducing friction and allowing waste to glide more efficiently into the trapway with less water. This seemingly minor detail had a profound impact on the overall cleaning effectiveness and reliability of the flush. Engineers also meticulously optimized the water spot size in the bowl, ensuring an adequate surface area of water was present to receive waste effectively before the flush, minimizing residue. While most commercial toilets with flushometers utilized a washdown action, where water swiftly pushes waste directly into the trapway, principles of siphonic action, typically found in residential tank-type toilets, were also refined. For commercial setups, this meant ensuring that the powerful washdown action, when coupled with the lower water volume, was still capable of generating sufficient kinetic energy to clear the bowl efficiently. The goal was to achieve a robust, single-flush performance that rivaled or even surpassed the efficacy of older, higher-volume models. To assure compliance and, more importantly, performance, independent testing laboratories and certification processes became increasingly vital during this period. Organizations like IAPIMO R&T, a division of IAPIMO, and CSA Group provided independent testing and certification services, verifying that fixtures met the 1.6 GPF standard and performed according to established criteria, such as those set forth by ASME. These certifications offered assurance to plumbers, contractors, and building owners that the products they installed would meet regulatory requirements and function as intended. While the Maximum Performance, or MAP, testing protocol, which provides a comprehensive assessment of a toilet's waste removal capabilities, would gain widespread prominence slightly after our 2000 cutoff, its foundational principles and the industry's need for such robust performance metrics were firmly established during this period of post-EP Act refinement. MAP testing, in essence, emerged from the necessity to quantify and compare the real-world performance of low-flow toilets beyond simply measuring flush volume. The transition also necessitated extensive educational efforts within the plumbing community. Plumbers, contractors, and building owners needed to be thoroughly educated on the nuances of the new 1.6 GPF technology, including specific installation requirements for flushometers, proper sizing of water supply lines to ensure adequate pressure, and best practices for maintenance. This was particularly crucial for flushometers, where the correct adjustment of the control stop and the integrity of the diaphragm were critical for optimal and consistent performance. Maintenance considerations for flush valves became even more nuanced with lower flush volumes. The precise operation of the diaphragm, the condition of the bypass hole, and the cleanliness of the control stop became paramount. Even minor leaks or obstructions could significantly impact the overall water efficiency and flush performance. Water quality, particularly in regions with hard water, also played a role, as mineral deposits could accumulate within the valve components, necessitating regular inspection and cleaning to ensure longevity and consistent operation. The move to 1.6 GPF was not just a manufacturing challenge, but also a significant shift in the operational and maintenance paradigm for commercial plumbing systems. The incremental progress throughout the 1990s was a testament to the industry's resilience and capacity for innovation. What began as a federally mandated challenge evolved into a sustained effort to not only meet, but to exceed the baseline performance expectations of water-efficient commercial plumbing. This decade solidified the 1.6 GPF standard as the new norm, paving the way for further advancements in the years to follow, built upon the lessons learned and the technologies refined during this critical period. Beyond the specific technological and regulatory changes, the period from 1970 to 2000 also brought forth significant broader contexts that influenced the incremental standardization of commercial restroom flush valves. The economic impact of these shifts was multifaceted. For manufacturers, the federal mandate introduced substantial costs related to research and development, retooling existing production lines, and investing in new machinery capable of producing the redesigned flush valves and toilet bowls. This often translated into initially higher unit costs for the new 1.6 GPF fixtures compared to their older higher volume counterparts. For builders and developers of public buildings, these higher initial fixture costs represented an added expenditure in construction budgets. However, these upfront costs were eventually offset by long-term savings for building owners and operators, as significantly lower water bills translated into tangible operational cost reductions over the lifespan of the building. The concept of life cycle costing, evaluating the total cost of ownership, including initial purchase, installation, maintenance, and operational expenses, began to gain prominence, highlighting the economic advantages of investing in more efficient plumbing fixtures despite a higher initial price tag. From an environmental perspective, the cumulative impact of these changes was substantial. Quantifying the national water savings achieved through the widespread adoption of 1.6 GPF toilets, particularly in high-use commercial settings, became a crucial metric. While precise figures are complex to calculate due to varying usage patterns and populations, it is understood that billions of gallons of water were saved annually across the United States. This directly contributed to broader sustainability goals, reducing strain on municipal water supplies, decreasing the energy required to treat and pump water, and lessening the burden on wastewater treatment plants. The connection between efficient plumbing fixtures and broader environmental benefits, such as drought mitigation and ecosystem preservation, became increasingly clear and widely accepted. The role of plumbing codes at both local and state levels was crucial in the enforcement and integration of the federal mandate. Once EP Act 1992 was passed, state and local jurisdictions were tasked with updating their existing plumbing codes to reflect the new 1.6 GPF standard. This process involved legislative action at the state level and administrative procedures at the municipal level, ensuring that all new construction and major renovations incorporated the federally mandated water-efficient fixtures. The model plumbing codes, such as IAPMO's Uniform Plumbing Code and the Building Officials and Code Administrators International, or BOCIA, which would later merge to form the International Code Council, or ICC, and develop the International Plumbing Code, or IPC, became vital tools in disseminating these new standards. These codes provided a standardized framework that states and localities could adopt, streamlining the implementation process and ensuring consistency across different regions, thereby further contributing to the standardization aspect of our discussion. It is important to emphasize what standardization truly means in this context. It does not imply a single, monolithic design for all commercial flush valves. Instead, it refers to the establishment of a common set of performance parameters, dimensional requirements, and operational criteria that multiple manufacturers could meet. This approach fosters competition and innovation while ensuring interoperability, ease of replacement, and a consistent level of performance across the industry. For example, a 1.6 GPF flushometer from one reputable manufacturer would be expected to deliver a comparable level of waste removal and water efficiency as a 1.6 GPF flushometer from another, even if their internal designs had subtle differences. This standardization benefits building owners and maintenance staff by simplifying procurement and maintenance. Knowing that a certain level of quality and performance is guaranteed, the incremental nature of these changes cannot be overstated. The transformation from high-volume, unregulated flushing to universally adopted, low-volume, standardized efficiency was not a sudden revolution. It was a continuous, deliberate process characterized by a series of small adjustments, iterative technological refinements, periodic regulatory updates, and ongoing industry adaptations. Each step, from the initial local water restrictions in the 1970s to the federal mandate in the 1990s, and the subsequent industry response, built upon the foundation of what came before. It involved countless hours of engineering design, materials science research, committee meetings, testing, and field adjustments. This steady, persistent evolution is a hallmark of the plumbing industry, where public health and safety, combined with practical functionality, necessitate a cautious yet progressive approach to innovation. The impact on the user experience in public restrooms also evolved over this period. Initially, some users encountered the aforementioned 1.6 GPF blues with early, poorly performing models, leading to frustration and the need for multiple flushes. However, as manufacturers refined their designs throughout the mid to late 1990s, the performance of 1.6 GPF commercial toilets, particularly those equipped with optimized flushometers and bowls, significantly improved. Users gradually adapted to the new flush characteristics, and the quiet evolution of this ubiquitous device became an accepted part of the public restroom experience. The focus shifted from concerns about performance to an appreciation for the subtle improvements in hygiene and the quiet satisfaction of knowing that less water was being used with each flush. As the millennium drew to a close, the industry had successfully navigated the initial challenges of the 1.6 GPF mandate. The stage was set for future advancements, with early discussions already underway regarding even lower flush volumes, such as 0.8 gallons per flush for urinals and eventually for toilets in the post-2000 era. The concept of dual-flush systems, offering different flush volumes for liquid and solid waste, was gaining intellectual traction, although widespread adoption was still some years off. Similarly, touchless activation technology, while still a premium feature, was becoming more refined, and its potential for enhanced hygiene in public restrooms was clearly recognized. These emerging ideas, though not fully realized within our 1970-2000 timeframe, were direct descendants of the groundwork laid by the incremental standardization efforts of the preceding decades. The technical specifics of flush valve design continued to evolve with each passing year. In the 1990s, the material composition of diaphragms, for instance, saw improvements. While natural rubber had been a staple, the industry explored synthetic elastomers that offered greater longevity, resistance to chemical degradation from water treatment additives, and enhanced resilience to repetitive pressure cycles. These material advancements translated directly into more reliable flushometers with longer service lives and reduced maintenance requirements, a significant benefit for building managers. Furthermore, the precision in manufacturing these components increased substantially. Computer numerical control, or CNC, machining, and advanced injection molding techniques allowed for tighter tolerances in the production of valve bodies, plungers, and diaphragms. This precision was critical for achieving the consistent flow rates and flush volumes mandated by the 1/6 GPF standard. A millimeter's difference in a bypass hole or a slight imperfection in a diaphragm's seal could significantly impact water usage and performance, making consistent quality control paramount. The plumbing engineering community also played an increasingly sophisticated role. As water efficiency became a primary design parameter, plumbing engineers became adept at calculating minimum required static and dynamic water pressures for new installations, ensuring that the building's water supply system could adequately support the performance of the new low-flow flushometers. They also focused on optimizing pipe sizing to maintain velocity and pressure, even with reduced flow rates, preventing issues such as sediment buildup or inadequate waste transport in drain lines. Backflow prevention, a critical public health concern, continued to be meticulously engineered, with the vacuum breaker component of the flushometer being continuously refined to ensure unwavering protection against cross-connection contamination. Trade associations, such as the Plumbing Manufacturers International, or PMI, served as crucial platforms for industry collaboration, advocacy, and education. They facilitated dialogue between manufacturers, shared best practices, and often worked with regulatory bodies to ensure that standards were practical, achievable, and beneficial. These associations often commissioned studies, developed white papers, and hosted seminars to disseminate knowledge about the new water efficiency technologies and regulations, accelerating the industry's collective learning curve. The subtle shifts in building codes at the state and local levels were a continuous process of integrating the federal mandates with regional specificities. While EP Act 1992 set the national floor for efficiency, some states or progressive municipalities chose to adopt even more stringent local codes, requiring fixtures that exceeded the federal minimum. This created a dynamic environment where the national standard was seen as a baseline, with local jurisdictions having the flexibility to push for even greater efficiency where local water conditions or environmental priorities dictated. The process of code revision, involving public hearings, expert review, and often contentious debates, underscores the democratic and iterative nature of standardization. Each update to a state or local plumbing code represented another incremental step in the broader march towards greater water efficiency in public buildings. The development of new testing protocols, beyond just flush volume, became essential. While ASME A112.19.2 and A112.19.6 provided the fundamental framework, the real-world performance discrepancies of early 1.6 GPF models highlighted the need for more comprehensive performance assessments. These assessments aim to evaluate a toilet's ability to clear various types of waste materials, its bowl cleaning effectiveness, and its resistance to clogging under conditions simulating heavy commercial use. This focus on performance beyond mere volume was critical in restoring confidence in low-flow technology and driving manufacturers to innovate further. The economic implications extended beyond direct water bill savings. Reduced water consumption often translated into lower energy costs for heating water in some applications, and reduced wastewater treatment expenses. For communities facing water supply challenges, efficient fixtures meant delaying or avoiding costly infrastructure projects, such as building new reservoirs or desalination plants. These broader economic and environmental benefits provided a compelling rationale for continued investment in water-efficient technologies and the ongoing refinement of standardization efforts. The history of commercial restroom toilet flush valves from 1970 to 2000 is thus a meticulous tapestry woven from technological ingenuity, regulatory foresight, environmental imperative, and economic pragmatism. It is a story not of dramatic revolution, but of steady, incremental progress, where each small adjustment to a diaphragm, each refinement in a bowl's glaze, and each consensus reached in a committee meeting contributed to a significant, yet often unnoticed, transformation in how we manage and conserve one of our most precious resources within the confines of our public spaces. This journey into the details reveals the profound impact of what might seem, on the surface, to be a rather mundane topic, illustrating how dedicated efforts towards standardization can lead to widespread and lasting positive change. The period laid the robust foundation for further advancements that would follow, ensuring that the humble commercial toilet continued its silent evolution towards ever greater efficiency and sustainability.